Section 3.4 is called motion on a ramp, but it could really just as easily be called axis systems can rotate. So what I'm trying to say by that is we're going to study the motion of a block on a ramp that has no friction. It's completely smooth. And if we look at a typical axis system, I'll move this one over to the side. If we look at a typical axis system, left, right, up, down, here's the x-axis, here's the y-axis. You could use this to study the motion of this block, but the block becomes a two-dimensional motion then. And here's why. If I draw a motion map for this block, it's going to get faster as it goes down the ramp. So it's accelerating this way down the ramp. Now, along this direction, it's only traveling along a line, so it's one-dimensional if you look at it along the surface of the incline. But if you're using a left, right, up, down axis system like this one, then you can see that the direction of motion and the direction of the acceleration is actually two-dimensional. This vector points a little bit in the x-axis and a little bit along the negative y-axis. But there's a solution to this. We can always rotate an axis system. So you could take this axis and rotate it so that the x-axis is along the ramp itself. This way, we don't have to worry about anything happening in the y direction. We just have to look in the x direction for the motion. Now, there's kind of a trick that occurs here for finding the acceleration of an object on a ramp then. And it relies on the idea that free fall acceleration points straight downwards. Now, if this object were in free fall, we know the acceleration would point downwards and that it would be a value of 9.8 meters per second squared. Now, that's not the acceleration of this object because it isn't in free fall. However, if the ramp is frictionless, and that's a big if, but if that were the case, you could take that downward acceleration of 9.8 meters per second squared, and you could take a look at its components, and its components in the x and the y-axis. So if this is the x component, we'll call this the x and the y. Likewise on this, x and y. The x component of the acceleration and the y component of the acceleration can tell you what the acceleration of the ramp will be. Now, we know there's no motion in the y direction, so the y direction, the y component of the acceleration doesn't tell us anything. But this x component would be the acceleration of the block along the incline. I can show that in the other slide here. So again, here's a big picture of it. Let's take an arrow, and we'll draw on a nice x and y component here. So the x component would look something like this. The y component would look something like this. That's pretty close. And you do end up having a right triangle. Now, if we want to break up this right triangle using trigonometry to find the components, we need to know an angle. So if I go back here for a second, the angle of the incline theta is also the angle that's going to be made between the y-axis and that acceleration vector pointing straight down. And there's a reason for it. I mean, if I draw an acceleration vector straight down here, this would complete a right triangle in here. I can even continue this straight down. So this angle, given that this is a right angle, has to be 90 minus theta, which makes this angle theta. So it might even be more helpful if I draw my triangle like this, because this angle in here is going to be theta. This vector is g, the free fall acceleration. This is the y component of the acceleration, and this is the x component of the acceleration. And this is the one that's going to tell me the acceleration of this object going down the ramp. So I could find this component it should be equal to g. And since we're looking at the side that's opposite the angle's theta, it'd be g sine theta, pointing down the ramp, whichever direction you choose that to be, plus or minus. So it's not a huge idea in terms of just the physics, this equation. The bigger idea is that you could actually manipulate the axis system and twist it so that it points in a way that's favorable to the problem that you're solving.